So, good morning all of you. Today in VLSI technology course, we will start a new section, that is diffusion. Diffusion is very important chapter in IC processing. I hope all of you are aware regarding diffusion phenomena. Diffusion is a natural process by which molecules of a medium moves from high concentration region to the low concentration region. The requirement for this particular mechanism is to maintain a concentration gradient. That means any medium, maybe gaseous medium or liquid medium, so there the molecules from high concentration region naturally will move towards the low concentration region until both the region concentrations are same. Equilibrium is reached. Till then diffusion will continue. So this phenomena is used in case of semiconductor technology to diffuse the impurity atoms into the semiconductor material. Now we will concentrate on discussing the impurity diffusion in semiconductors. Diffusion provides a powerful means of introducing controlled amounts of chemical impurities into silicon. Controlled amount is very important term here, because until unless you can control the diffusion process, then you will not have any control on the impurity concentration into the silicon layer. So you have to have certain arrangement so that you can control the amount of dopants which diffuse into the semiconductor material. This particular technique which we are going to use in VLSI process are ideal for manufacturing of the VLSI chips, because in this particular process is highly suitable for batch fabrication. That is one of the important aspect when you are manufacturing in a large number. Batch processing means you can process large number of wafers at the same time in the same sequence. Okay. Dopant diffusion in silicon is done from three methods. What are those methods? They are namely diffusion from a chemical source in a vapor form at high temperature. Second is diffusion from a doped oxide source, and the third is diffusion and annealing from an ion implanted source. All the three methods we will discuss, and all these methods are used in integrated circuit processing. Diffusion from a chemical source in vapor form, that means that chemical source may be liquid or may be gaseous. If it is a gaseous, so it is already in vapor form. You can easily flow those gases into a furnace called diffusion furnace, where the wafers are kept and diffusion can continue. But if the source is liquid, then you have to have certain arrangement for changing the liquid into its gaseous form, and for that we use bubbler, and I will discuss bubbler arrangement in detail when I will discuss pure shell 3 diffusion. And the second is diffusion from a doped oxide source. Sometimes a doped oxide, that means oxide layer which is doped with impurity atoms, are deposited on silicon surface, then the substrate, means silicon substrate along with the doped oxide are kept in a high temperature diffusion furnace, so that from the doped oxide the dopant atoms will penetrate into the silicon or diffuse into the silicon surface, and it will diffuse deeper into the silicon, and the conductivity of the silicon layer is changed. Okay. So, that is diffusion from a doped oxide. So, there we use sometimes boron diffusion from doped oxide, or arsenic or some other impurity atoms may be diffused from a source, and the source may be in oxide, doped oxide. Now, the third one is diffusion and annealing from an ion implanted source. That is a totally different technique by which we implant the dopant atoms, and after that we anneal it at high temperature, so that the dopants will redistribute and they will enter into the silicon. It's blank. I don't know what they are doing. ये की problem देखो. Yeah. Now diffusion and annealing from an ion implanted source, that particular thing we will discuss in detail in ion implantation chapter. Now, diffusion mechanisms. Silicon is a single crystal material, and that single crystal silicon we in wafer form, we diffuse impurity atoms into the single crystal structure. Silicon is a diamond crystal structure, and in this diamond crystal structure how the impurity atoms move, that we will see, and there are different mechanisms available by which the impurity atoms diffuse into the silicon crystal, and those mechanisms one by one we will discuss. And yeah, here is the diagram which shows the interstitial diffusion, and in this particular diagram the green circles are silicon lattice points. They are separated by a lattice distance, okay, crystal lattice distance, that is from one lattice point to another lattice point, that distance is uniform over the entire bulk single crystal silicon. And now the in between the silicon lattice points, those are interstitial sites, and now the impurity atoms, they will move from one interstitial site to the other interstitial site. Here the red marked dot is dopant atoms, and they are moving from one interstitial site to other interstitial site by jumping, and from the next interstitial site to the next by jumping. In this way, from here to again here, from here again here, they are moving in this fashion. Okay. So, now this technique is known as interstitial diffusion. Here this jump rate, that means movement of the impurity atom from one interstitial site to other interstitial site, is given by nu equal to 4 nu naught exponential minus em by kt, where nu naught is equal to frequency of lattice vibration, that is silicon lattice solid that at a particular temperature that vibrates, and there is a frequency of vibration of the lattice points, So that is nu naught, and Em is the interaction energy, and this interaction energy value is in the range of 0.6 to 1.2 electron volt, and the jumping frequency of the dopant atoms from one interstitial site to another interstitial site is 10 to the power 13 to 10 to the power 14 per second. Okay, that is the jumping frequency. Now, this jumping movement or movement of the impurity atom from one interstitial site to another interstitial site is dependent on temperature, and it has been observed the jump rate is once every minute. That is normally the frequency of jumping at room temperature. But obviously, if you increase the temperature, the jump frequency or jump rate will increase. And in this particular mechanism, the dopant atoms which are smaller in diameter, those dopant atoms follow this interstitial diffusion. For example, if the dopant atom diameter is more than the interstitial site dimension, then it cannot accommodate the interstitial site, and it cannot jump from this side to this side. So, smaller atomic diameters are from group 1 and group 8. This should be group 8, not group 7, wrongly printed. So, group 1 and group 8 material, and the diameters of those atoms are smaller than silicon host atom diameter. So, that is why they can move from one interstitial site to another interstitial site. Next mechanism is known as vacancy or substitutional diffusion mechanism. Vacancy or substitutional diffusion mechanism. So, that is shown here in this diagram, and here the for occurring this vacancy or substitutional diffusion, you have to create certain vacancy sites. Here what happens, by any reason, if a silicon from a particular crystal lattice site silicon is absent, so that particular site is vacant, and that may be the defects, and which are known as Schottky defects, and those Schottky defects may act as a vacancy site. Now, a silicon atom, if it is absent from a particular site, then that particular site will be occupied by a dopant atom. That means it is substitution. The dopant atom is substituted the silicon atom. Now, again, the silicon atom can move from one lattice site to another lattice site, and obviously the dopant atom follows, means it will again jump from one of the vacancy site to the next vacancy site. That means when the impurity atoms move from only one vacancy site to another vacancy site to the next vacancy to the next in this fashion, then it is known as substitutional or vacancy diffusion mechanism. Here the jump rate, that means movement of the dopant atom from one site to another site, that is given by the equation here. You see nu equal to 4 nu naught exponential minus En plus Es by kT, where nu is the frequency of jumping and nu naught is the lattice vibration frequency. En is potential barrier to break certain covalent bond, because until unless the covalent bond is broken, so you cannot get a particular site blank, so that impurity atom will come there, and the Es is energy of formation, and K is Boltzmann constant, and T is temperature in absolute scale. So, here the jump rate is found once in every 10 to the power 45 years at room temperature, you can imagine. So, in 10 to the power 45 years, only one jump rate, that means one vacancy site to another vacancy site, the impurity atom will move. that is obviously at room temperature. That means we can say at room temperature, in fact, there is no diffusion, isn't it? This particular mechanism is highly suited for group 3 and group 5 dopant atoms of silicon. That is most favorable. Okay. Now, in actual practice, in our diffusion process, we found that a lot of diffusions are taking place. That means that is taken at high temperature. That is very important. But room temperature, there is no diffusion. If you increase the temperature, and normally the temperature is in the range of say 900 to 1100 or 1200 degrees centigrade. So there, the jumping frequency increases quite a lot. Okay, this is also clear from this equation, nu equal to 4 nu naught exponential minus E naught plus Es by kT. Okay. Now, the third one is known as interstitialcy diffusion or interchange diffusion. What is this mechanism? That is shown here. Interstitialcy diffusion, here basically the interstitial site, the impurity atom moves to the vacancy site, and from the vacancy site the atom moves into the interstitial site. You see, an impurity atom, when it is in the interstitial site, they replace one silicon atom from lattice site, and that silicon atom will move to the interstitial site, and this lattice site is occupied by this dopant. That is one type. Another type is the silicon atom move from one interstitial site to other site in this fashion. That is also possible. And then interchange is also there. That means a particular dopant atom, when occupies a particular lattice site and another neighboring lattice site, say silicon, is occupying, then the silicon and the dopant atom, they may interchange each other. That is also movement of the dopant atoms. So that means all sorts of movement are known as interstitialcy diffusion. Here, a host or an impurity atom displaces a lattice atom, which in turn becomes an interstitial atom. This type of diffusion is dependent on the availability of vacant sites and occurs at a slower rate than interstitial diffusion. In this mechanism, two or more atoms diffuse by interchange process. Okay, that's why it is also known as interchange diffusion. So that is interstitialcy diffusion. Okay, and there is another one which is known as the Crowdian mechanism. Fourth one is Crowdian mechanism, and that is just some sort of interstitial mechanism. So it is another form of interstitial diffusion, is a Crowdian mechanism, and there you can see the atoms, impurity atom moves from this interstitial site to the another interstitial site, and the silicon atom moves from lattice sites to interstitial site. So that means here the movement not irregular, so regular movement, and that is the middle of the interstitial site. This is the impurity atom. It pushes the silicon atom to the next interstitial site, but it will also be at the middle region, middle line. So a related interstitialcy mechanism is Crowdian mechanism, in which an interstitial atom is located halfway between two lattice sites, halfway between two lattice sites. It migrates into one of the lattice sites and displaces the lattice atoms, which becomes an interstitial atom at the halfway position. That means it is another form of interstitialcy mechanism. Only the movement is from the halfway to another halfway between the lattice points. That is the difference. Okay. And the fifth one is known as interstitial substitution diffusion. That is basically the combination effects. Interstitial substitution diffusion is like this. Here, combination of interstitial and substitutional mechanisms may occur within the crystal. Some of diffusion atoms may finally end in substitutional sites, with others in interstitial sites. Both interstitial and substitutional diffusion occurs in this particular mechanism. If Ns and Ni are substitutional and interstitial solubilities respectively at the diffusion temperature, the effective jump frequency is given by nu effective, which is nu S Ns by Ni plus Ns plus nu I Ni by Ni plus Ns, where nu S and nu I are substitutional and interstitial jump frequency, and Ns and Ni are given by are basically substitutional and interstitial solubilities. What is the solubility? Solubility means at a particular temperature, the maximum number of atoms which are accommodated in the crystal lattice, that is known as the solid solubility. In a solid material, means crystal, single crystal silicon here, at a particular temperature, a definite number, a particular number of silicon atoms, silicon dopant atoms can accommodate there. Okay. So, that is known as solid solubility limit, and the effective jumping frequency is given by this expression. Normally, Ns is large compared to Ni, but nu S is small compared to nu I. Thus, the second term is much larger than the first term. Because of this inequalities of Ns Ni and nu S nu I, the second term is much larger than the first term. Okay. So, basically in diffusion furnace, when diffusion takes place, which type of diffusion mechanism is predominating is very difficult to conclude. Any of these interstitial or vacancy or substitutional that may take place in combined manner. You cannot separate out. So, this much amount of dopant atoms are because of interstitial diffusion, and that much amount of dopant atoms are because of substitutional diffusion. This is a combined effect. But only thing we can say from the atomic size of dopant atoms, that whether it is favorable for the substitutional diffusion or it is favorable for interstitial diffusion. Obviously, in case of interstitial diffusion, the dopant atom size should be much smaller than the silicon atom. Otherwise, the favorable mechanism is vacancy or substitutional mechanism. But all the mechanisms are involved in actual diffusion process. Next, we will switch over to diffusion theory. We discussed mechanisms of diffusion. Now, we will look into the diffusion theory, and we will derive some of the equations which describe the diffusion or doping concentration, which is a function of temperature and time. So, in 1855, Fick published his theory on diffusion. The theory is based on the analogy between material transfer in solution and heat transfer by conduction. Heat also transfers from high temperature region to the low temperature region, that is by conduction mechanism. Similarly, in a liquid material transfer in a solution, material means you are aware that in a for example a sugar solution, if you a membrane if you put in a solution, and membrane one side is high concentration sugar solution and other side is a low concentration sugar solution, then from high concentration side sugar molecules will pass through the membrane till the concentration of sugar on both sides are equal. That is osmosis type of thing. So that is from those ideas and also the heat conduction mechanism, Fick established the diffusion theory. Diffusion occurs due to the concentration gradient of dopants, I told you earlier also. In addition to diffusion, ionized impurities can move in presence of a drift field. In steady state, the drift velocity is given by Vd is equal to mu into E. Mu is the mobility and E is the electric field. That means one cause of movement of the dopant atoms into the silicon lattice, bulk silicon lattice from one lattice point to another lattice point is the concentration gradient, and other than the concentration gradient there is another reason of movement, that is the electric field. Why? Because the dopant atoms are ionized when they move from one point to another point. They are charged particles. Obviously, they will be affected by electric field. Okay. Now, let us discuss Fick's first law. Fick's first law states that in the presence of electric field, flux density is given by J equal to minus d del n del x plus mu E n. Here there are two terms. One is basically proportional to del n del x. Another is proportional to the drift velocity because of electric field. And drift velocity is given by mu E. Mu is the mobility of the carriers, and J is the flux. That is the number of molecules per crossing per unit area per unit time. So that is the flux. So flux is proportional to 1 del n del x, and flux is again proportional to the electric field. So now when you equate it, then J equal to d del n del x. This d is known as diffusion constant, and this diffusion constant is a function of temperature. Now all the parameters here are described. J is flux density, it is atom per centimeter square. E is electric field. Mu is mobility of impurity ions, that is centimeter square volt second. D is the diffusion coefficient, centimeter square per second. N is volume concentration, atoms per cc. X distance in centimeter. And in this particular equation, D has taken out of this differential because we assume D is constant. But this is not always true. D1 is function of temperature, no doubt, and D is also function of concentration. If it is function of concentration, then you cannot take this D out of this differential, because with distance, x is the distance, that is vertical distance from the surface of the silicon crystal. So with that x variation, the concentration varies, and if the concentration of the dopant varies, the D also changes. But for simplified analysis, we can assume that this D is concentration independent, and we have taken out from the differential. So if D is constant, then and in the absence of the electric field E, so then this equation reduces J equal to minus del n del x. Now why the minus is given? Because if you increase x, concentration reduces, because it moves from high concentration to low concentration region. So with x, n reduces. N is the dopant atom concentration, volume concentration of dopant atoms, which is atoms per cc. So now since it is it decreases, So that's why negative sign is given. Okay. Now let us derive the expression for this flux. Now this is a small cross section, a small section of a silicon atom, say rectangular section we have considered here, and this rectangular bar A is the cross sectional area, and these are two planes, one is at x and other is at x plus dx. These are the two planes, and J is the flux. So at plane x, the flux total number of dopants coming in the plane A is A into Jx. A is the surface area, and Jx is the flux at point x. The definition of the flux is number of atoms per unit area per unit time. So in area A, it is A into Jx. Okay. So that the total number of atoms, I call impurity atoms as atoms. The impurity atoms reaching at the plane at x is A into Jx, and say at x plus dx, the number of impurity atoms crossing out of the plane is A Jx plus dx. Jx plus dx is the flux at plane x plus dx. Clear? That means flux in is A Jx, and flux out is what? A into Jx plus dx. So that difference, this is incoming and this is outgoing. So difference of that will remain inside this incremental volume. And what is the incremental volume between x to x plus dx? Is A dx. So that is the volume. And if the rate of increase of the impurity atom in this particular volume is del n del t, isn't it? So rate of increase of incremental volume, incremental concentration of these dopant atoms is del n del t. So that means A dx del n del t will be equal to A Jx minus A Jx plus dx. Okay. Now next few steps are like this. So del n del t from the earlier equation we can write as Jx plus dx minus Jx. The same equation is written in different way. Okay. That is equal to minus del J del x. Okay. Now here if you replace J, because J in equation 1 is given by J is equal to what? Capital D del n del x. This J is equal to capital D del n del x. Now if you replace the value of J here, then this equation comes as del n del t is equal to del x of D del n del x, because one negative sign was there in J expression and here another negative sign, so automatically this is positive. Okay. So now again we assume that the D, capital D, is concentration independent. So you can take this capital D out of the differential. So now del n del t is equal to D del 2 n del x square for constant D. Okay. So now equation 2 gives nxt with proper boundary condition and initial condition. This is known as second law, Fick's second law. Fick's first law is a J equal to D del n del x. Now the second law is the time variation is also coming, del t, del n del t, isn't it? So there this n is a function of both time and distance in xt. Okay. Now, this equation you can solve with proper boundary condition and initial conditions. So, we will solve. There are two diffusions. One is known as diffusion from a constant source and diffusion from a limited source. Boundary conditions in both this diffusion theory, diffusion process are different. Boundary conditions are different. Now, in this particular case, diffusion from a constant source, and is also it is known as constant surface concentration diffusion. That means dopant source is constant. Concentration of the dopant source is not reducing with time. That's why it's known as the constant source diffusion. And that is the example of pre-deposition diffusion, where Ns is equal to N surface and is equal to N solids solubility. And in this particular case, wafer is exposed to an impurity source of constant concentration during the diffusion period, in case of diffusion from a constant source. Okay. Examples of this diffusion is emitter diffusion, ohmic contact diffusion, etc. All pre-deposition diffusions are diffusion from a constant source or constant surface concentration, because in this particular step the wafers are in a close proximity to the diffusion source, and if it is a solid source are kept near the wafer. If it is a liquid source, then the liquid source in the form of vapor is flown into the diffusion furnace, so that throughout the process the silicon wafers will be in contact with the source material. So, that is the silicon surface. At the surface of the silicon, the dopant atoms is the N solid sol or N surface, which is constant throughout the diffusion time. That is the pre-deposition diffusion. Now, the initial condition for this particular diffusion mechanism is at t equal to 0, nxt is equal to nx0 equal to 0. That means at t0 means at the beginning, initial time, that's why it's not initial condition, and there the concentration is 0, where at x is greater than 0. What is x? X equal to 0 is the silicon surface. Silicon surface is x equal to 0. If you go deeper into the silicon, then x is greater than 0. So, that means inside the silicon crystal at the very beginning there is no impurity atom. That's why at t equal to 0, nxt equal to 0 for x greater than 0. Now, the boundary conditions. Boundary conditions for a constant source diffusions are namely n0t equal to ns, and the second one is n infinity t equal to 0. What are the implications of these two conditions? First is at x equal to 0, that means at the surface, for any amount of time, any time t, whether after diffusion process starts, after that at any length of time, at the surface, which is n0t is equal to ns. Ns is the surface concentration. That is the constant source diffusion. Okay. And the second one is at x equal to infinity. That means at a larger depth of the silicon crystal from the surface, the impurity concentration is 0. That means at the surface it is maximum, at the surface it is maximum Ns, and at a larger depth from the surface the concentration is 0. These two conditions, if you apply the Fick's second law, then you can solve that Fick's second law equation, and you will have the doping concentration, which is nxt is given by ns ERFC x by 2 root dt. That is the solution. Using the initial condition and boundary condition, these two boundary conditions are known as Dirichlet condition. If you solve this second order differential equation, then its solution is given by nxt equal to ns ERFC x by 2 root dt. ERFC is a complementary error function, and the complementary error function is given by 1 minus ERFZ. ERFC z equal to 1 minus ERFZ, where ERFZ is the error function and 1 minus ERFZ is complementary error function. And complementary error function is given by this relation ERFC z is equal to 2 by root pi into e to the power minus x square dx, and this is from 0 to 0 to x. Integration limit is from 0 to x. If you integrate it, ex square dx, and it's multiplied by 1 by root pi. This is known as ERFC z. ERF z, the error function z or complementary error function z are not in closed form, and you have to consult the lookup tables or standard curves to find those values under certain conditions. That means here what you have to do, you have to find out the values, and then for those values, then x by 2 root dt, then you have to consult some table. So from that table you will get the ERFC values, complementary error function values, and then you can have an idea of nxt. Okay. So this is the diffusion from a constant source, and the doping profile equation is nxt equal to ns ERFC x by 2 root dt, and ns is the surface concentration, d is the diffusion constant, small t is the temperature, and the capital D is the diffusion constant, which is a function of temperature. That means this nxt, this profile, is dependent on time and temperature both. This profile depends time and temperature. Temperature comes through D, capital D, diffusion constant. Okay. Now let us look into the profile. Concentration profile of a constant source diffusion is like this. For different values of dt, for under root dt equal to 0.15 micron, 0.2 micron and 0.25 micron, the concentration profile looks like this. This is the complementary error function curves. Here you see whatever dt value you set, the surface concentration is constant, and here the concentration axis, the y axis is concentration, the ratio basically, the C by Cs, C surface is surface concentration. Here it is 1, 10 to the power 0 is 1. So 1 means here the concentration is equal to surface concentration. You look at the figure. So at x equal to 0 here, at x equal to 0, the concentration is surface concentration. And if you increase the time, that means this small t. Again, if you increase the temperature, that means you are changing the capital D. So for those values, we found that at x equal to 0, the concentration remains constant. That is a constant source diffusion. At the surface, dopant source is constant. Now with time also, with x equal to infinity, it will be 0. So this is the x axis, that is depth. x equal to 0 is the surface is here. If you increase x, that means you are going deeper and deeper from the surface at a larger distance from the surface of the silicon. Okay, at a larger depth. Now, this is the complementary error function profile, and which agrees with the pre-deposition diffusion. Here you can see one blue line, and the blue line is NB, which is a background concentration. That means a silicon, if a silicon is say N type, and then you are diffusing P type dopant, and the P type dopants are diffusing here. That means up to certain depth here, for example, if dt equal to 0.15 micron, up to this is a P type dopant is more, and below that particular point is a N type dopant, because basic substrate was N type substrate, as I told you, and you are diffusing P type dopants, isn't it? So that means where will be the junction? Junction will be this point, because if you concentrate on the first curve, then the profile with distance reduces. That means profile means what? The concentration reduces. So up to that particular point, the boron or P type is more, and after that distance N type is more, because it is less and will dominate will be the N type. So here is the junction. In this way, in diffusion, junctions are also formed. Now, next is the limited source diffusion. A limited source diffusion is another name, constant total dopant diffusion. And in this particular class of diffusion, it agrees with the drive-in diffusion. And examples for these diffusions are base diffusion, low surface concentration, and deep diffusion are examples of limited source diffusion. In this particular case, the source from the surface is removed. The diffusion source from the surface is removed, and then whatever the dopant atoms existed on the surface of the silicon, those will be redistributed into the larger depth of the silicon. That's why it is known as limited source. The source is limited, it's constant. Whatever source has incorporated in the pre-diffusion diffusion, that particular amount of impurity atoms will diffuse further. I mean, they will redistribute further into the larger depth of the silicon atom, so that the profile will change. That is known as the limited source diffusion. And in this particular diffusion, a finite quantity of the diffusing material is first placed on the wafer. Diffusion proceeds from this limited source, and is assumed that all of this matter is consumed. That means in this particular class of diffusion, the dopant atoms are redistributed, but total dopant atom will be constant, because from the external, no extra dopant atoms are coming into the silicon. Whatever it was there, and those will redistribute, and diffusion profile will change, and because of that, the total dopant will be constant. Okay. Now here the initial condition is at t equal to 0, the nx0 equal to q naught delta x. Nx0 equal to q naught delta x. That means here at the beginning, like earlier case, the dopant atom is 0, we cannot say, isn't it? So in this particular case, at the beginning, at t equal to 0, nx0 equal to q naught delta x, and boundary conditions are del n del x 0 t equal to 0. That means here at 0 means what? X equal to 0 is surface. So at the surface, the concentration is constant. So that's why del n del x at the surface is 0. And here again, at infinite time, the nx, any distance, it will be 0, means it is minimum. Then it will redistribute further and further, and ultimately the impurity atoms may may disappear at infinite time, large time. Another boundary condition is nxt dx equal to q naught is a constant. The integral of nxt dx q naught is a total dopant that is constant, and these conditions are not known as Cauchy's boundary condition. And if you use this initial condition and these boundary conditions in the fixed second law, then the diffusion profile and solution of that is nxt q naught divided by under root pi dt. Okay. So I will next class I will start from the same slide and will continue this diffusion, that is constant total dopant diffusion. Okay. Thank you.